Hi, my name is Andrew Niles. I'm an applications engineer at ON Semiconductor. Today I'd like to talk about the new NIS54XX evaluation board. The NIS54XX is a new line of eFuses. eFuses are devices used for storage protection applications. The NIS54XX series includes the NIS5452, 5451, and 5431. These devices have many features, such as overvoltage protection, adjustable current limiting, over temperature protection, a controlled slew rate for the output voltage, as well as an enable pin that has a fault indicator function. In addition to that, this new lineup of eFuses has very low RDS on. It's only about 30 milliohms, and this allows the devices to remain very cool even in high current applications. Here we're testing the NIS54XX evaluation board. I'm just going to take a second to explain the setup. Here we have a DC power supply set to 5 volt input. We're actually testing the NIS5452, which is intended to be used with a 5 volt power supply. Here we have an oscilloscope with 4 channels. We're going to be measuring the input voltage, the output voltage, the total input current, and the enable pin voltage. The NIS54XX is in the center of this board here, and we can see that we basically just have an input cable coming from the power supply and also a ground, and the current is being measured on the input. Looking at the oscilloscope here, the yellow line is the input voltage, or the VCC pin of the eFuse. The blue line, which is just underneath the yellow line here, is the source or output voltage of the eFuse. And the pink line is the input current, but right now there's no current flowing, so that's just at 0. And the green line is the enable pin voltage, which is in its high state at about 3.5 volts. Now we're looking close up at the evaluation board itself. The eFuse is right here in the middle. It's very compact. It's in the WDFN 3x3 package. So the width and length of the device are only 3 millimeters. There are several components around the device. These are just used to help show some of the features of the eFuse. Starting in the top left, there is an input cable connector, another DC jack, and 3 more input connectors just for convenience. Here there's an enable pin indicator circuit. Right now the enable pin is high, so a green LED is showing. If the enable pin goes low, for example if it goes into thermal shutdown, then an orange indicator LED will be showing. Just below the enable pin indicator circuit, there's a capacitor for the controlled output slew rate feature. It's selectable with this jumper here. There are also 3 current limit resistors available that are selectable with a jumper. In addition to that, there is an enable pin switch so that the enable pin can be grounded if the device needs to be reset after entering thermal shutdown. There's also some jumpers available here to control the enable pin with an external MOSFET or other device if needed, although a MOSFET is also included on the board for that purpose. Over on the right-hand side of the board, there's a ground connector. This is a ground connector in addition to another ground connector on the left side of the board. Either one can be used, they're connected. There's also an output capacitor that is selectable with a jumper, in addition to 2 load resistors. So for a 5 volt operation, 1.5 amps can be drawn on this board. If additional current is needed as a load, that can be done by connecting a load using this yellow connector here. Also on this evaluation board, there is a switch for shorting the output. So in case the current limiting feature needs to be tested, just press on this button and the device will limit the current after observing that there's a short circuit condition. And at that point, the green light that is on when the output voltage is high will turn off. First, we're going to show the overvoltage protection feature of the eFuse. The NAS54XX eFuse has been designed for very rapid overvoltage protection. Usually it's under about 5 microseconds. Here we're just going to show the basic functionality of it. So what I'm going to do is change the input voltage, the VCC line, from 5 volts up to about 10 volts very quickly, and we'll see the output voltage being limited to about 6 volts. So I'm getting my oscilloscope ready to trigger. I'm going to turn the input voltage up, and we'll see that the output voltage is limited. So here we can see the yellow line is the input voltage rising, the blue line is the output voltage staying to the same level, and there are no issues at all. And this overvoltage protection feature is very important for protecting downstream components that might not be able to handle voltages above about 6 volts. The eFuse has a built-in thermal shutdown feature. If its internal temperature exceeds 175 degrees Celsius, it will automatically shut down. This relieves concerns about the safe operating area of the internal MOSFET. There are actually 2 ways for the device to enter into thermal shutdown. One is if an excessive current has been drawn. Another is if there's excessive input voltage on the device and the output voltage is held to the V-clamp level while current is flowing. To show that, what I'm going to do is place jumpers on the load resistors on the evaluation board. That will allow some current to flow. And then we're going to increase the input voltage and observe the device go into thermal shutdown. So right now it's conducting 1.5 amps at 5 volts. We're going to increase it, and I'm actually going to set my oscilloscope to trigger on the enable pin going downwards. So we're going to see it actually enter into thermal shutdown. So first, the input voltage is rising, the output voltage is being limited, and then all of a sudden the enable pin dropped to 1.4 volts. And we can see back on the evaluation board that the orange indicator light on the board is on. In order to reset that, one thing that we need to do first is to lower the input voltage to make sure that we don't run into the same condition again, and then just push on the enable pin reset button. Now the enable pin is down at 0, we release, and the output voltage will come back up. And the device is conducting 1.5 amps again. Another way to enter into thermal shutdown is to accidentally have a short circuit on the output. We'll go ahead and show this here now. Right now the eFuse is conducting 1.5 amps. If the switch on the output is pushed, this current will rise up very high. We'll see that right now. So there's a lot of bouncing in the switch, but basically the eFuse detects the current, shuts it off very rapidly. The response time is around 10 microseconds. It's very fast. It's been tuned to do that. After some time with the switch bouncing, the eFuse will limit the current to this level here, which is about 2.5 amps, but this level and the initial trip level are adjustable with current limiting resistors on the evaluation board. And we can see again that the device has entered into thermal shutdown. So we can go ahead and remove the fault and reset the device, and we'll see everything come back to normal. So unlike a one-shot fuse, the eFuse is capable of being reset without any damage having occurred. After an eFuse has entered thermal shutdown, there are a few different ways that it can be reset. One way is to bring the enable pin voltage to 0 and then release it. This is typically done with an external transistor or, in the case of this evaluation board, a push-button switch. Another way to reset it after it has entered into thermal shutdown is to cycle the input power. That would mean bringing the VCC voltage from 5 volts down to an intermediate level and then bringing it back. What we're showing here are the latching version of the 54XX. There's also an auto retry version. For example, the NIS 5452 MT2, and that device, after it has entered thermal shutdown, will actually try to reset itself. And if the fault has been cleared, or if there's no longer an overvoltage event, that device will continue to operate normally and will not require any external intervention.
Okay.
This device is capable of being hot plugged so it is suitable for hot swappable applications. It also has a controlled output voltage slew rate feature, which we are going to show here. So my power supply is set to 5 volts, but the device is not connected yet. I'm going to set my oscilloscope to trigger, plug in the power cable, and we can see here that the input voltage rose. The output voltage also rose a short time later, and there was no issue. One feature of this device is that the output voltage slew rate is adjustable with a capacitor. So we're going to show the difference putting a capacitor in versus this case, which did not have the capacitor, and the output voltage came up in about 1.4 milliseconds. So now the output voltage came up nice and slow. This is about 150 milliseconds.